I work at Intel and I run our Ethernet business, and I wanted to say thank you to Albert and Deepak for having us and inviting us to be here today. I think that's a great idea to have a forum like this and get together and be able to exchange ideas, and I already appreciate what I learned this morning. Oh, I need the clicker. Okay, so I work at Intel. This is going to be a little more of a hardware-focused talk, but I think it ties in really, really well to what we heard this morning. So Intel's been selling Ethernet controllers for 30 plus years, but I think this is an especially exciting time to be in this business because the hardware underpinnings of the things we talked about this morning are starting to really, really change the products that we're building. And for somebody with a CPU background, it's pretty exciting. So let me talk first about the key inflections that we're seeing. This echoes a lot of what we heard this morning. So we see optimization at the platform level. We see cloud service providers looking to offload some of the infrastructure work that they do in their Xeon compute cycles that they could potentially be renting out. The problem of cloud scale, the opportunity of cloud scale, we've talked about that a lot this morning. You know, the CSPs are getting bigger, fast, very, very fast, and the network has to keep up. It's got to be performant, it's got to be flexible. And then last but not least, critical workloads like machine learning are really changing the way the network works as well. So instead of these vast pools of general purpose compute, the network is changing to support these specialized accelerators. A little bit more about that. So on the left side of the slide, you see the networking configurations of today mostly. So Ethernet, it's flexible, it's configurable, it's universal, and it's served us well to connect data centers at the pace of scale that we've had in the past. For more high performance compute like meteorology, genome sequencing, workloads like those, we have high performance fabric, so Omnipath and InfiniBand, if you're familiar with those. Those are optimized for performance, for low latency, quality of service, and they run in these specialized systems. So moving into the future, I think we're going to see a lot more of these accelerator pools with anywhere from 16 to thousands of nodes. Think of GPU Direct, for example, and those will be connected with tight interloop fabric that's optimized for those workloads, potentially needs access to memory and storage at higher bandwidths than what we've seen traditionally. And all of those nodes, all those clusters will be connected by Ethernet. And Ethernet in the future has to get more and more performant, take on more of the attributes of what we've traditionally called high performance fabric. So low latency, high throughput, better bandwidth, all those kinds of things. So as we look at our roadmap, those are all things that we're working to drive in the future. Okay, so I'll be getting to SmartNICs here shortly, but let me talk just a little bit more about the motivation behind them before I explain what they are for anybody that doesn't already know. So driving workloads off the CPU onto these SmartNICs comes about from a number of different things. So we have the agility that was talked about a bunch this morning, how quickly new services are being deployed in the cloud, how flexible and reliable and available these networks need to be to support the kinds of things you all talked about this morning. That's a big, big challenge for us. And you know, you can only upgrade an Ethernet controller and the physical hardware so often, but you really want to change what's running on top of it much more frequently. Infrastructure as a service. So in this business model, people rent out the cores, they monetize them, turn them into you know, things that the customer can rent and monetize. And so the more Ethernet speeds are increasing, the faster the network is getting, 25 gig and above. As a percentage, more and more of what we call the data center tax, things like storage, networking, security services, all those things run in software on the Xeons and take up valuable compute. So if we can move those things off Xeon class servers onto SmartNICs, it results in better TCO for the CSPs. And then last but not least, for these special workloads that we talked about before, we want to be able to have better performance, and the SmartNIC will help with that. Our SmartNICs will have better latency, will have particular hardware-based acceleration that will speed up specific workloads. So Let me talk a little bit more about what that might look like in particular. So on the left-hand side of the slide, you'll see a traditional infrastructure as a service configuration, virtual machines, the hypervisor, infrastructure workloads like storage and networking, crypto and compression. All those things run in software, take up space on the CPU, may or may not be particularly optimized, and may or may not be particularly flexible. And then in the platform, you'll have a traditional NIC that's transporting data around. But as we move into the SmartNIC era, one of the first offloads that's become easy and obvious to do is VirtIO. So right now, if you run VirtIO on a Xeon server, you get about 2 million packets per second. When we optimize that in hardware, we're seeing that we can potentially improve that by an order of magnitude. So it's a great candidate for an offload. You can partition this function, and you can move it into a SmartNIC to run either in fixed silicon, like an ASIC, or on an FPGA. From there, we expect to evolve that into storage and start moving fast path and potentially eventually slow path storage onto a SmartNIC as well. So then you've offloaded a pretty good chunk of your infrastructure data center tax. And then crypto and compression, if you're familiar with these workloads, they're really compute intensive, they're power hungry. Those are also great candidates for something to have a hardware-based accelerator for, where the hardware is really optimized for those functions, and move it out of the Xeon. We have an emerging use case here, a bare metal server. I'm sure you've all heard about that. And this is where a tenant rents the entire physical server. Instead of having a virtual machine, you rent the actual box, and it's your box, and you can do with it what you want. You get great isolation, but all the infrastructure stuff that would have otherwise run in the Xeons now runs on the SmartNIC, so that you really truly get an isolated box. And it protects people from performance losses and migration, noisy neighbors, yields better total cost of ownership, and enables things like a cloud within a cloud, third-party hosting, and it simplifies the private cloud. So the question mark just means the tenant has this, they can run whatever they want, and there's nothing in there that the CSP is running. CSP's moved everything that they need to maintain their infrastructure and their business model off the CPU itself. Okay, so what's in a SmartNIC? This is, on the left-hand side is the traditional host, and you see all the workloads, security, storage, networking. It's all running in software on general purpose Xeon cores. And so as we move to SmartNICs, this is a picture of a bare metal example, and you'll see all the cores in the middle, and they're free to be rented out. They're free to be used, they're free to be monetized. And we've moved all of the infrastructure workloads onto the SmartNIC. So one of the benefits, obviously, is freeing up your Xeon cores. But another thing is that SmartNICs are really programmable. They're flexible. We bring a number of different assets together in a SmartNIC, FPGAs, ASICs, and cores. Cores are programmable through software. FPGAs can accelerate functions in hardware for better performance at some amount of power and cost. But people can make those trade-offs and bring those assets together and make the right mix for whatever their particular application or workload is. Yeah, I guess the other thing I'd say is they can have really high throughput because you can optimize the hardware for specific functions. Okay. So when we look at the potential applications for SmartNIC, I think this is a super dynamic space. We talked to a lot of customers about it. It's a bit of a greenfield. It's not exactly clear. There's not a one-size-fits-all. Different customers want to optimize different things. Different workloads are more important to them. They have different ability to deploy certain kinds of solutions. And so this mix of assets in the hardware to be able to achieve these goals is really critical. The high-performance data planes are really best benefited if they stay in fixed function logic, so either in an ASIC or in an FPGA. Macs are a good example. That's the Ethernet controller. Crypto and compression, those are really specific kinds of workloads that really lend themselves to hardening the IP in an ASIC or an FPGA. Things like match action pipeline, connection tracking, packet processing, things that are a little bit more flexible, that are more dynamic, that are changing as the workloads in the cloud change, things that you're going to have to configure and update often. Those are great candidates for running on the cores in software. But the partition between these is still evolving. There are a number of different solutions in the market, and in talking to customers, we see lots of different optimization points for different usage models. So it's I would say the hardware underneath, there's not a certain formula that I'll talk about today. It's more an emerging picture of different capabilities, different optimization points, and different kinds of hardware acceleration that can solve for a particular challenge that the customer has. Okay, so let me just talk a little bit more about an FPGA versus a core. FPGA, field programmable gate array. I think probably most of you would know what that is. So it has logic blocks, it has I/O, and you basically program the gates to make the function that you want. It's an array of gates, and so there's potentially some efficiency loss versus having an ASIC, but it's still going to be much more performance optimized than running everything in software. The other nice thing about an FPGA is that for TTM, it'll be really, really excellent for people because you can reprogram your FPGA when you need to, as opposed to waiting for an ASIC. So say you have special telemetry needs, for example. If you want to run those in hardware and get some optimization on an FPGA, you can program that whenever you need a change. If you want to put that function in an ASIC, you have to wait a year and a half, 2 years, whatever the ASIC development cycle is. So for things that are changing, FPGAs are a really, really great option. We are seeing now some embedded acceleration capabilities in the FPGAs, more and more so, specialized engines in there, like a DSP, for example. So we see kind of the FPGAs merging over to going more in the direction of ASICs as more and more things get hardened over time. And then the core runs software. So the cores are high performance. They have really great single-thread throughput. Most of the cores in a SmartNIC would be single-thread type cores, not multi-threaded cores. And if you have a complex design, you have complex software, you have things that are changing really, really fast, this is potentially a really good option. And then there's a rich ecosystem already because a lot of these workloads have been running in cores, in the Xeon cores, and can be ported over. So we talked about partitioning, functional partitioning, moving things off the Xeon cores into the SmartNICs. So that's functional partitioning, but that will also drive real physical change at the platform level. So as we move these workloads into SmartNICs, they're moving onto a different part of the platform. The power budgets change, the thermal budgets change, things become more distributed at the platform level. And the next generation of OCP, we're seeing power envelopes of 75, 80 watts and up to accommodate the fact that these SmartNICs will sit in these cards. They'll have compute on them. They'll have accelerators on them. They'll have FPGAs on them potentially. And so they need more space. They need more power. They need more of the thermal budget. Long term, so when we look at SmartNICs today, I've talked about a lot of different hardware that could be in a SmartNIC. We see combinations of all those different things as options. But over time, we're going to want to do what we did on the other side, which is to start integrating those functions into a SmartNIC, harden more and more of the functions in an ASIC, have fewer and fewer different components so that we start to drive those power budgets back down again, drive the thermal budgets back down again, and just create more thermal and power headroom on the machine. And then, so I talked a little bit about the hardware that's underneath all of this. The big challenge for us, I think, will be once the hardware starts to stabilize, how do we bring SmartNIC solutions to the masses? Right now, these are definitely the domain of CSPs. That's where we spend most of our time with our customers, learning about usage cases, figuring out what's needed. But in order to deploy one of these right now, you need to have a really capable engineering team. You need to have enough bandwidth, enough engineers to do it. There's quite a software lift to make this work. And there's a lot of innovation happening even as people are deploying them. They're learning more about their workloads. They're changing things all the time. When we talk about requirements, we just get new information on a weekly basis. So this is an incredibly dynamic environment driven by the CSP requirements at this point in time. But over time, we're going to want to bring this to enterprise. We're going to want to bring it to pretty much anybody with a data center. But not everyone is going to have the capabilities that the CSPs have to be able to do the engineering that's required to be successful with this. And so this is a little bit of a call to action. I think I'm probably speaking largely to a software audience, and we need the industry to evolve with us and be able to build a software stack on top of these SmartNICs that can be democratized, that can be used by others with less engineering bandwidth and potentially less technical savvy, people that from OEMs and people building data centers that just don't have a large technical support staff. So we're looking for better SDKs to run on top of them. We need innovation on the orchestration side so that these can be really deployed effectively. They're not going to be as cheap as a regular Ethernet controller, and not everyone can realize the benefits of these if they're not a CSP today. So if you can't deploy them efficiently, you're not going to get the same use out of them. And then last but not least, so DPDK is you guys all know what that is, and now we have storage performance development kit too that we're working on, and we need that to be able to be optimized and run on the SmartNICs and port over from the CPU. So in summary, I'd say, this is a super dynamic environment. It's an underpinning of the networking challenges that we talked about all throughout the morning, this really dynamic environment that's running on top of a network that has a lot of evolving left to do to be as performant, as flexible, as manageable as is needed for the scale of cloud innovation and the specialized compute that we also talked about. So, I think it's a super exciting time for us. I think the conversations we're going to have here today, hopefully over dinner and throughout at the panel, will help our team to understand more and more about what's needed, help you guys to understand more how we can make these things more usable for the rest of the industry. And I think we'll see this evolving at a really, really rapid pace for the next couple of generations. So, okay, that's what I had. That went faster than I planned. So I'll take some questions if you have them. I can hear you, yeah.
The question is, you've described something that is extremely flexible and can be deployed towards several different target applications, okay? How do you test for all the corner cases on something that's that flexible, particularly in a NIC application? So some of our experiences are, you can set something up, you hit a corner case and say 8% of the population falls out on this particular corner case. So it's not a design error, but it's a device error. How do you test for that in your high production environment?
Yeah, that's a great question. How do we test for all the different corner cases? We talk about flexibility, we talk about how much space we want to cover with these. So how do you make sure that you get every usage case that might possibly exist? And I'll tell you, we have not solved that. I think the way we're approaching this is in chunks. So we have, in particular, VirtIO. We understand, we're really customer focused with these things, first and foremost. So we focus on the customer usage case. We try to understand who our initial target customers are, what they're going to need, and we really focus the testing on that. And ideally, we have, and we do have some partnerships with particular customers to test in their environment and really do. It's really a co-innovation model for us because, like I say, these requirements are dynamic. They're changing. The people that use them are learning what they need. And so, working side by side with the customer is really critical. And narrowing, we can't possibly cover every possible space initially. So that's how I'd answer that question. Any other ones? Yeah.
Hi, Patty.
Hi.
As someone who formerly worked with Intel's LAN access division
wow.
a number of years ago, one of the things that kind of came to forefront with us when we were trying to do the TCP/IP offload engines was that exception processing required a lot of kickback out to the host CPU. And it's interesting when you brought up bare metal in the talk today, and I'm wondering if you have any thoughts of how much power is going to be actually required, how much computational power is going to be required to handle these links when they're running 100 gig Ethernet, 200 gig Ethernet, 400 gig Ethernet, and beyond. Are we going to have the capabilities to be able to power that? And is that going to be a good balance between, we kind of came, this was over 10 years ago, so I'm dating myself here. But we kind of came to the decision that TCP/IP offload engines weren't efficient cost-wise because the CPU was actually much better at it. Now that we're getting into these FPGAs with SoCs and stuff like that, are we going to discover that same thing, or do you guys feel that you can get that to a cost and power efficiency that's better than what we can do with CPUs today?
I'll give you kind of a general answer, and then if our CTO wants to jump in, he's welcome to. But if we can,
I know him well.
You know him?
I do not need to talk.
I don't know if you believe anything he says then, but
I don't.
If we can turn it into a hardware accelerated function, into a specialized function that we can run on an FPGA, or that we can harden in an ASIC, because there will be variants of SmartNICs. Some will have ASICs hardening in ASICs, some will have FPGAs. If we can turn it into that, then I think it scales much better. If you're running it in a general compute kind of way, then less so. I'm more worried about the core scaling at 200, at 400, probably more 400 than 200. All right, at some point, that core complex, because it is a general purpose complex that supports software, we may well have problems of scaling that we haven't solved yet.
Okay.
Do you want to add anything to that, Yuri? Or?
I'd just say,
you go to the mic.
Come speak in.
This is Yuri Cummings. He's a CTO for our group.
if we think back long enough, we do kind of remember the TCP/IP offload debates. And I think one of the things that was sort of maybe the wrong way of approaching that back then was that we weren't looking at, it was more of a bottoms up than a tops down. So when we offload software, we want to kind of look at, if I take this function and I put it in another system and then create a different type of interface to that system, does the overall system work better? But when you have, when I take like a TCP stack and I run some of it in like a hard NIC and then I leave some of it in software, I haven't really offloaded the TCP stack. I think that was the basic problem that we had back then. Plus the CPUs got so much better at networking that it just kind of washed that all out. When we look at SmartNICs today, we're looking at a system that's really grown up. And so we do think that we will see new ways of making the network more efficient through offload and acceleration.
Yeah.
Okay, thank you.
You mentioned hypervisor services, right? Does that mean that all the hypervisors will have to be changed in order to take full advantage of this? Or is that services that would be able to be accessed from the host OS, for example?
Yuri, do you want to take that one?
In your slide, it showed hypervisor services.
I mean, yeah, I mean, they have to be ported to the, go ahead. Yep.
The slide was pretty generic, so I was trying to give you sort of a high-level overview. In reality, with a bare metal server, all it means is that there's a significant sandbox up to, but probably not including the the root of that system that the customer could use. They could run their own virtualized hypervisor on there. They could do anything they want within that sandbox. And that says, yeah, CSP hypervisor services. Now, on the other hand, what the CSP might want to do is put some aspects of that hypervisor into a SmartNIC, like a DOM0 or something, but that's really a design decision of the CSP or whoever the hoster is in this case. It really isn't specified by the SmartNIC itself.
I see. Okay. Another question, if I can. The FPGA, is that only reprogrammable so that you can optimize on the fly, or is that you have to turn off and then back on?
Will it support live migration?
Will it support like on-the-fly reprogramming of the FPGA so that you can optimize your network dynamically?
I don't think we can reprogram it without entirely on the fly yet, right?
Yeah, the intent is
Yeah.
to be able to reprogram it while it's deployed. You don't have to bring the server in.
Right.
So there is mechanisms to load an image and switch over really quick.
Okay. Okay. So you do have to kind of flip it.
You do. You do. You do.
Right. Cool. Thank you.
Yeah.
What are your thoughts on network specialized cores on the NIC instead of?
Network specialized cores, great question. You know, I think we'll get there. I think we're starting to see some specific features we want in our general purpose cores, but this is just still dynamic enough that I think an entire network specialized core isn't going to be general purpose and flexible enough to meet the needs of the market today. That said, you know, I think we will see some specific core modifications in our general purpose cores for networking. Yeah.
Kind of an extension of the last question, but more specific. So you're essentially saying vSwitch, so OVS, which is pretty popular in CSPs and East-West and
Right.
VXLAN encapsulations. But do you got to be there to leverage this offload, or is there? I mean, should we be looking at doing an OVS under our value add, or are there going to be other variants we can offload? I guess. I mean, does it have to be
You mean, does it
vSwitch?
have to be OVS or other?
Yeah.
No, I don't think so.
Okay.
No. No, it's the VirtIO interface that gets optimized in hardware. So I think you can run different kinds of vSwitches on top of
Okay.
that.
All right. So
Yeah.
we're not going to be excluded if we're not doing OVS.
No, no. That said, that is the common use case, right? But it's not specific to that.
So you talk a lot about this acceleration kind of being in the upper end of scale in the Xeon class and stuff like that. Do you guys see value and market for some of this stuff in the lower thermal footprint, lower scale lines of CPUs as well?
Yes. I mean, we have a line of SoCs that have atoms in it, and they run networking workloads, they run storage workloads, so some of that is happening. But they're more standalone boxes than paired and running offloads like this is. This, I would say, is more tightly orchestrated at the platform level. Any other questions?
Yeah, I had one question here. It's related to the bump in the wire that the gentleman just talked about in some of the TCP offload. Is there any thought given to zero copy operations for network data at all? Because one of the biggest problems that you have the NIC running really fast, and then the OS slows everything down because of buffer copies that occur. And so I'm wondering if anybody's given any thought to zero copy.
Yeah, Yuri, go ahead.
I mean, do you mean like an RDMA service or?
Less RDMA, but DMA to the service. Yeah, you could consider that as an RDMA, I guess.
Or a DMA from the host into the
Correct.
into the SmartNIC. Yeah, I mean, I think a lot of that gets into the sort of detailed implementation of the product, but clearly the performance between the application and infrastructure services that are running on the SmartNIC is critical. And so we'll do we'll have features and we'll do a lot of testing work to optimize that performance.
Any other questions? I know I'm the last thing between you and lunch. Okay, thank you.
Okay, thank you, Patty. So we'll now take a break for lunch. We'll be back at 1. The lunch is outside, so please help yourself and see you again.